last time we talked about Laplace's equation. So specifically, this is known as the Laplacian or the Laplace operator. And so now when you set Laplace u equal to 0, that's known as Laplace's equation, or the Laplace, whatever you want to call it. So I have right here, when we set Laplace u equal to 0, that's very traditional PDE that everyone loves to solve, including yours truly. So here is the two-dimensional problem. So now, what's a little tricky, and you should go slow and take a minute to think about, is we're shifting gears. In Laplace's equation, time, t, is not involved. This is a steady state calculation. This is a PDE that, has the PDE is only in the spatial variables. We talk about partial u, partial x, partial u, partial y. X and y are spatial variables. So we don't have initial conditions, we have boundary conditions. And so there's two strategies here. So first of all, just, for this rectangular domain, we have our boundary conditions on each side of the rectangle. And so the strategy for solving this is to divide and conquer. So what we'll do is use the fact that the Laplacian is linear, and we'll put two of these boundary conditions here as non-homogeneous boundary conditions on one problem, and we'll put the other two boundary conditions on another problem as non-homogeneous boundary conditions. And in each case, we have a set of boundary conditions that are homogeneous in this divided problem. And so the basic idea is to say, okay, let's decompose our solution u as u1 plus u2, where u1 is going to satisfy this problem here. And based on our theory, this is a problem we can solve because the Laplacian, that's linear. If any two functions satisfy Laplace u equal to 0, then their sum will as well. And if any function satisfies Laplace u equal to 0, then the scalar multiple times that function will also satisfy Laplace u equal to 0. And here, these homogeneous boundary conditions here, also have this vector space structure that if any two functions are homogeneous on these boundaries, if you add them, you'll still preserve the homogeneity. And so using that, we should be able to, in theory, using these two pieces of information that Laplace u is linear, these are nice boundary conditions, we should be able to do separation of variables. And when you do separation of variables, we have coefficients that we need to solve for. And so this is what we use the other set here of non-homogeneous boundary conditions. We use these boundary conditions kind of like the way we use initial conditions in the heat equation, but keep in mind, these are not initial conditions. And so in theory, we can solve this PDE, and the other PDE will go exactly the same way. The structure is identical, except that the variables have flip-flopped. Here we have this homogeneous boundary conditions here when y equals 0 and y equals h, as opposed to in the other problem, we have homogeneous boundary conditions when x equals 0 and x equals capital L. And here again, we use the non-homogeneous boundary conditions to solve for the coefficients. We use the non-homogeneous boundary conditions kind of like initial conditions. So then we do separation of variables. We do the traditional separation of variables assumption, assume u equals f times g, but right off the bat, we get something that looks different from heat equation. Here, this part doesn't look different. The equation in the x variable is the same as when you do heat equation with homogeneous Dirichlet boundary conditions. But The other problem, so remember, we do not have a time domain problem. So in the y variable, we get this second order ODE that basically is, looks identical to this second order ODE up here. In one case you have lambda, in one case you have minus lambda, but the overall form is the same. So we know from experience and wisdom, let's not discount wisdom, people, that the solution to the F equation here gives us this, the basis is these sine functions with eigenvalue we can calculate to be n pi over L squared. This is purely because of the boundary conditions. And this is nothing new. The G equation here is slightly different because this is second order. So we make this usual assumption about the solution form that it has this exponential form. And so now here, we do a little bit of mathematical manipulation. And I wanted to highlight, we talked about it, but let me just highlight here. When it comes to these non-homogeneous boundary conditions, what we're going to do is we're going to plug in y equals 0 in our formal solution and set the formal solution equal to f of x. And then hopefully when I set y equal to 0, what I'm hoping to get is some kind of Fourier series. And then we're also going to set y equal to h, set that thing equal to f2, and hopefully when I set y equal to h, I get a Fourier series, okay? So we want to set up the solution so that parts of it will go to 0 when you plug in y equal to 0 or y equal to h. That's all kind of being arranged in the background. If you just straight solve the ODE, the basis of the solutions is this set of exponential functions. But then you can take linear combinations. And so we can get a new basis. We can get cosh and sinh. So here, from this basis, I take new linear combinations, and then I get cosh and sinh. But again, we don't like this because we want, one of these terms to disappear when y equal to 0, and one of these terms to disappear when y equals capital H. Right now, when y equal to 0, sinh will disappear, no problem, wonderful. However, if we let y equal capital H, cosh will not disappear, neither will sinh. So it's not quite where we want it. And so we're going to just do some math trickery. We have a hyperbolic identity, which allows us to write sinh of n pi y minus h as a linear combination of our basis elements. So here's a sinh n pi y, here's the cosh n pi y. Those are our basis elements. These other two terms, this is just a constant. H is fixed, L is fixed, pi is pi, n is one of our numbers, of our index. So again, this is just a constant. What you should see is a linear combination of basis elements so that this function combined with sinh forms a new basis. So now finally, we get to where we're trying to go. We get to this new basis for our solution. And what's nice about sinh of n pi y minus h over L is, well, if we let y equal capital H, you get sinh of 0, which is 0. That was the whole point. Here, if you let y equal to 0, the sinh will disappear. Here, if you let y equal to h, the sinh n pi y minus h over L will disappear. So now we've got everything in the form that we want that will be mathematically convenient. So finally, we formulate our solution to the G equation in terms of sinh n pi y over capital L and sinh n pi y minus capital H over capital L. So yeah, now product solutions. Product solutions. So here, we now combine our F equation solution, which is just our sine function, and all this hyperbolic stuff. And so here's the F equation solution. So that's coming from F sub n right here. And then here's the rest of it. You know, I distributed the F equation solution across the G equation solution. So here's the G equation solution. Then superposition, right, the linear combination and adding them all up. And here, this U sub 1 that I'm referring to, this is the solution to that first set of PDEs that we have. So here, the notation is a bit not great, but you know, I don't want to add more superscripts and subscripts or something, you know, so from context, I think hopefully we're okay. So now, you know, the whole reason we did all this manipulations with the hyperbolic functions is we can now, you know, like I said, when you let y equal 0, the a sub n term disappears. Only this b sub n second term survives. And if you take a look at all of this stuff here that's being multiplied to the sine n pi, b sub n is a constant. N pi h l are all constants. So this whole term we can just think of as being, just think of that as another constant, call it, you know, b sub n tilde. And so now we have a Fourier sine series. We know from the orthogonality of the sine basis, we can find a formula for b sub n tilde. I replace, remember, b sub n tilde is actually b sub n times sinh negative n pi h over L. So you divide by the sinh negative n pi h over L to solve for b sub n. So groovy. And now we do the same thing. We plug in y equal to h. The sinh n pi y minus h term disappears. Only this a sub n term in the front here survives, and you replace the y with h. Again, what we see is a Fourier sine series. I can use the orthogonality to solve for a sub n tilde. And then, you know, a sub n tilde, I can divide out the constant to solve for a sub n. And so then we've solved 1/2 of this Laplacian problem, you know, where we're looking at the boundary conditions when y equals 0 and y equal to h. So boundary conditions at the top and bottom of the rectangle. So then for the other problem, it's exactly the same. So this is the part that, you know, you should take a minute and appreciate that this problem is actually kind of easier than the heat equation. Because this problem for U2 is basically the same problem as for U1. The only difference is the role of the x and y variables have changed. Now we have homogeneous boundary conditions when x equals 0 and x equals L. Before we had homogeneous boundary conditions when y equals 0 and y equal h. So it's the same problem. Here, the only difference is, okay, here I've written lambda, here I've written minus lambda. That doesn't really change anything. This ODE will still have trivial solutions in certain situations and non-trivial solutions in certain other situations. And because of the sign difference between the minus lambdas, the situations are flip-flopped. So here, the only case where we have non-trivial solutions is when lambda is less than 0. For the F equation, it was when lambda was greater than 0. So at the end of the day, when we solve for G, we should get the same solution as when we solved for F in the U1 problem. G should be sine n pi y over, you know, L, instead of you're just kind of changing the roles of the X's and Y's, the H's and L's. So I'll let you think about that. I won't rehash it, but you know, we've solved this problem already. We've just changed the variables, the G's and the Y's, the G's and the F's, the X's and the Y's, the H's and the L's. You know, other than that, it's still the same problem. So yeah, so here I have this sine term that we're expecting with our usual eigenvalue, except the h has been turned on L, x has been turned on a y. And then we do the same kind of analysis. We want a solution for the f equation where the terms will disappear when you let x equal 0 and when we let x equal capital L. And so by using identities and by taking linear combinations of basis elements, we can rewrite the solution to the f equation in this, relatively messy looking hyperbolic linear combination of these hyperbolic sinh functions. Whew. All right, folks, so now we have the solution to the U2 problem, and we can find the coefficients in exactly the same way using the, orthogonality, Fourier sine series, all that stuff that we love. And so finally, we put it together into one huge solution. We do U1 plus U2. So here, I'll let you think about why this works, but linearity is, underpinning the whole thing. And so here we have our solution. That is your formal solution. Take a second to really see what you're looking at. Here, the only unknowns are these coefficients. Also, watch for the variables. Here's a y, here's an x, here's an x, here's a y, here's y, x, x, and y. Watch for the variables. The coefficients, as you know, we'll find out the coefficients from the data. So here, this is coming from the boundary information, right? So here, all of these coefficients, we use the boundary information to find, what the deal is with those. And that's really the only work we have to do in terms of setting up the solution, is to figure out what the coefficients are. Once we've laid out the canonical form, of the series solution, once you've identified, oh, this is Laplace u equal to 0 on a rectangle, so the solution should look like this, and now we can find the coefficients using the boundary conditions. So this is where we stopped last time. And one thing I want you to notice is this formal solution, the way it's set up, it's always 0 on the corners. And so I wanted to make a comment about that that's not necessarily true of our data, though. What if we have a situation where, our data is not 0 on the corners? So I'll talk about that in the next set of slides here, but just notice here, if you plug in 0, 0 or L, 0, 0H, LH, this thing always shuts down to 0. So just some final comments here, is that we can use this method to solve Laplace's equation in any, the two-dimensional version in any set of coordinate systems that are orthogonal. So you have your rectangular, your polar. I don't know if you're as familiar with the ellipse and hyperbola. So sometimes this is a problem that's done in a calculus class, is to show that the ellipse and hyperbola are actually orthogonal curves. But let me just draw this really quickly for you. So here we have, here's an axis. So here, what we can show just using, regular calc 1 is, let me try and draw a nice purple. So there's an ellipse. And here, let me try and draw a decent hyperbola. Yeah. Okay, it's already terrible. So here, right here, if you look at the tangent line, so if I look at the tangent line of the hyperbola and look at the tangent line of the ellipse, look at the tangent line right where they intersect, these are orthogonal. So here, these form a 90-degree angle. And so you can create a whole coordinate system with ellipse and hyperbola. So you have the ellipses centered, all bunch of ellipses, and then we have our hyperbolas, whole bunch of hyperbolas. And you can identify anything as being at the intersection of some hyperbola and an ellipse. Anywho, we won't get into that, but just talk about that. So as I mentioned, we have some zeros at the corners, which I'll talk about how do we address that issue in the next set of slides. So these next couple of points are all things we're going to talk about in the future. So the maximum principle is something we'll discuss in the next set of slides. So we'll discuss it maybe today, probably not. We'll get to it on Friday. So here, if we have a closed connected domain, the solution of the Laplacian equation will achieve its maximum and minimum on the boundary. If the maximum or minimum is attained in the interior, not on the boundary, then it'll turn out that the entire solution will be constant. So just hold off for a second on thinking about this too much. I'm going to do a little experiment that'll make a little more sense. Also, there's another part of this that says if you pick any point inside the domain, that point will be the average value of all the values in a circle around it. And again, don't worry about it. We'll talk about that here shortly. This is all topics coming up. And of course, we want to talk about convergence and issues like that. So this solution turns out to be bounded on the boundary and infinitely differentiable. And it'll turn out that the solution will converge absolutely. And its derivatives will as well. So all of that will come up now here in the next set of slides, which was posted early this morning, I believe. So here we go. Let me switch over now to the second set of slides on Laplace's equation to talk about convergence and also Laplace's equation on polar coordinates. So now I want to finish talking about the formal solution of the Laplace equation on the rectangular domain, and then start talking about it in polar coordinates for circular geometry. Some of the uniqueness proof is easier in polar coordinates. And in polar coordinates, we get some nice results that aren't necessarily readily obvious when we look at the Laplace solution in rectangular coordinates. So the circular geometry is nice because it does give us a little bit of intuition, a little bit more information. So this slide was just meant to remind you of what the Laplace operator looks like. And so now, essentially, what we want to do is talk about the formula for Laplace equation in terms of polar coordinates, and then how do we solve it. And actually, you already did on homework number 1, there was a problem that basically had you calculate Laplace in terms of polar coordinates. So here, I'll go through that derivation very quickly. I won't spend too much time on it because you did it as a homework and it was, painful then, and we don't need to go over it now. So just be careful. The book does this a lot. They use this bad notation. They say u of xy equals u of r theta, and that's technically incorrect. U of r theta is the same function as u of xy. We've just replaced, the x's and y's. I did this example last time. Suppose u of xy is x plus y. U of r theta then will be r plus theta, but r plus theta is not the polar form of the function. Here, x, we should really be replacing x with r cosine theta. And y we should be replacing with r sine theta. So to say u of xy equals u of r theta is just bad notation. My preference is they should use a different letter here or put a tilde on top just to indicate it's not the same formula. It's just the same function, but in different coordinates. So this is more appropriate to write. If we want to write anything, you can write u of xy equals u of r cosine theta comma r sine theta. Okay, that I'll accept. This is good. This is good. But to, equate that to r theta, that's not right. So that's not good. So anyway, I'll let you think about that. And so here's what I think is more appropriate. That here you can replace in u of xy, you can replace x with r cosine theta, great, y with r sine theta, no problem. And this will now give you a function that has a new formula. You know, if the original formula is x plus y, this won't be x plus y anymore. It'll be r cosine theta plus r sine theta. We call that this new variable u tilde or v. And now this is the same function. These two are the same function, but in different coordinates. All right, I'll let you think about it. It's just kind of this little ticky-tacky kind of technical notation stuff. So anywho, let me just, before I'm sorry, that was a little premature. I talked about the polar stuff. I want to finish up this stuff on the rectangular coordinates. So here, with regards to convergence, we can show algebraically this result that if A is less than B, and they're both positive, A is less than B, then we can show the sinh of NA divided by the sinh of NB is less than e to the n times A minus B. And so, and here, if A is less than B, then A minus B will be negative. So if here, if A is less than B, then A minus B will be negative. So if, you know, n is, you know, integer 1, 2, 3. So here, this is e to a negative number. So this will be less than 1. And as n goes to infinity, this exponential term will shut down to 0 very quickly. So the next question is, okay, well, where do we have a quotient of sinh? So if you look at our formal series, if you look at A sub n down here, we've got two parts to this. We've got the numerator, but the numerator looks just like a Fourier coefficient for a heat equation, or, you know, for just a regular Fourier sine series. And we know that that numerator coefficient term is well behaved as long as f2 of x is piecewise smooth. The part that's extra is down here. We're dividing by this sinh n pi h over L. And, you know, in the actual formal solution, look, I have a sinh n pi y over L. So right here, actually, if you look, so let me use a darker color here. So if we take this term divided by this term, remember the a sub n is right next to it. So that term is in here in this a sub n term. Then I get a quotient of these sinh that we're talking about. So, you know, what's going on here in terms of convergence is that the a sub n term, for the numerator, I'm not worried. We know if the numerator, if f2 is piecewise smooth, the numerator is well behaved. This sine n pi xl term, this term is bounded by 1. If I'm trying to show absolute convergence, if I take, you know, if I do a triangle inequality and take the absolute value, I know this part is bounded by 1. This part is not an issue. I can bound it by 1. It's the a sub n and the sinh terms, I need to know what's happening with those. So like I said, with the numerator of the a sub n term, as long as f2 is piecewise smooth, there's no problem there. The issue is what's going on now here with this sinh n pi y over L term divided by the sinh n pi h over L. And so what I'm claiming is that this inequality, which we can prove just using algebra, implies that this quotient of sinh is being dominated by this exponential term that's going to decay to 0. At the end of the day, this quotient of sinh is kind of like our decaying exponential time term in a heat equation, although it does not involve any of the variables of our PDE. There's no x or y variable up here, but n is going to infinity. So here, a minus b is negative, and here n is blowing up to infinity. So this is like e raised to negative n, you know, and n is going to infinity. So the whole exponential shuts down to 0. So if we can show this inequality, which we can, it just involves algebra, then we have a way of bounding the quotient of these cinches with a decaying exponential term. We can then, you know, get rid of the sine n pi x term. You can bound that with 1. The rest of it is going to 0 as long as the boundary data is piecewise smooth. We should be able to get very strong convergence here. Because at the end of the day, you know, it turns out that this, even though we don't have a decaying exponential term, this quotient of cinches, which appears in every term, acts like a decaying exponential term. It can be bounded by a decaying exponential term. And so the only part of it that I'm worried about, it's no issue. We can, you know, we can show that that shuts down as n goes to infinity very rapidly. And if you look, every one of these has an exponential term. So, I mean, a cinch, here's a cinch here. And in b sub n, in the denominator, you have a cinch. If you look at, here's a cinch with the c sub n term, and in the denominator, we have a cinch. And then here, for this last term here, you can see there's a cinch term here, and there's a cinch down here. Again, you know, x here is between 0 and L. So here, x minus L is always going to be positive, you know. Here, you can pull out the minus or do some tricks with minus, or you take an absolute value, you know. So we can all bound all of these things by some type of decaying exponential function. And that's what makes the convergence really strong. So it's all about this inequality. And we'll talk about, you know, how you show this inequality and then how you use it. And as I said, it's pure algebra to show that inequality. It's not, you know, with a few hints, you can get it quite straightforward, quite easily. So I want to talk about, you know, as I mentioned here, if you look at this formal solution, it's 0 on the boundaries. So here I say vanishes at the corners. What I mean is if you evaluate the formal solution at 0, 0, L0, 0H, LH. So remember here, our domain is this rectangle, and you know, we've got 0 down here. I forget which one's H and which one's L, but anyway, you can look at the picture. So what if we have data though that does not disappear at the corners? So there's an easy fix. What we can do is we can define this. It's a plane. If you think about your Calc 3, this is just x, y, x, and x times y here. This is a constant. And so this is just describing a plane. And what we can show is that the plane satisfies Laplace u equal to 0, because if you take 2 derivatives, this is basically a linear object. You take 2 derivatives, it's going to differentiate to 0. Here, A, B, C, and D are, you know, the data that we have on our corner, where I'm assuming it's not 0. So here's some corner data that's not 0. And so those are the letters that are showing up here. L and H, those are from the boundary, you know, for the domain. So we can show Laplace of capital U of this plane is 0. And if you evaluate the plane at the corners, we get the boundary data that we're looking for. So here at the corners, this equation of the plane matches with our boundary data. So now the trick is to make a new PDE using this substitution. Let V equal U minus capital U. This PDE will be a PDE that satisfies Laplace V equals 0. It'll satisfy Laplacian, the Laplace's equation, because of linearity. And we can find boundary conditions using the boundary conditions from U. For example, I did a sample calculation. So if I want to know the boundary condition when y equals 0, V of x0 would be U of x0 minus capital U of x0. And now U of x0, we know this boundary condition. That's given as being F1 here. And we know capital U of x0 is A. And so now I've found a boundary condition for V. And in that way, I can find all 4 boundary conditions and set up a new PDE. However, for the function V, it is 0 on the corners. We've engineered it so that if you actually evaluate V at any of the corners, here I just did 0, 0, for example, by definition, you get it's equal to 0. So I can find V using separation of variables, and I'll find basically this solution, but instead of U, it'll be V's. And so I can find V, I can add U to it, and that'll be what capital U to V, and then that'll be our final, our solution for little u. So here I can find V, and here I can take minus U, move it over. So add capital U to V, and that'll give me my, original function little u that I'm trying to find. So I've spelled it out here. So if U of X has a non-trivial boundary condition, define capital U as we've specified up here. Let V be little u minus capital U. Find the PDE for V and solve that PDE using separation of variables. And then add capital U to V to get the solution of our original equation, little u. So, I'll let you think about it, but I don't want you to worry about this slide too much. It won't come up. I just wanted to mention it as a technical detail because it is a fact of the formal series solution that it disappears on the corners, that it's equal to 0 on the corners. So, if you have data that doesn't do that, then we have to have a way of resolving it. So this is one way certainly of fixing it. It's a very kind of, just a cheap technical fix using the linearity. So I'll let you look at that and think about that. But as I said, don't worry about it too much. Here, we're going to mainly focus on just, solving Laplace, the Laplacian. I'm not too worried about these little details. So that kind of concludes our discussion of the Laplacian in terms of Cartesian coordinates. What we want to do now is to look at circular domains. Why? Well, because, in practice, we don't know what type of domain you'll find typically if you're trying to model a PDE. And so we should be familiar with all types of domains. Certainly circular is fundamental, but also because in polar coordinates, we get some nice results that we don't necessarily see obviously when you look at the solution in Cartesian coordinates. So of course, this all starts with converting Laplace's equation from Cartesian coordinates in the x and y variable to polar coordinates in the r and theta variable. So let me make a couple of comments, and I don't want to spend too much time on it because you did the derivation in homework number 1. So the comment I want to make is, in x and y coordinates, we know Laplace u is in 2 dimensions, is u partial x plus u partial y. And so here's the big mistake or the thing to not assume. So, this is not equal to the Laplace equation in polar coordinates isn't just u partial r plus u partial theta. That's again, that's just kind of replacing one symbol with another. We haven't actually changed anything. We haven't found the Laplace in new coordinates. Okay, so what we really need to do is to be very careful and do a chain rule here. So here's what we're going for, and I don't want to go into too much detail because you did a lot of this chain rule stuff. Here's at the end of the day, that's what the Laplace looks like in polar coordinates. And no, this is not a typo. So this is u. This is referring to the Laplace in terms of x and y. So this here, this would be, u partial x plus u partial y. That's your usual Laplace in rectangular coordinates. And now I'm saying, oh, in polar coordinates, it looks like this. And as you see here, I've used a different u tilde because it's not technically the same formula, but it represents the same information. So there's two basic chain rules. And here, the way we do this is backwards. It's not trivial. In the homework, what I had you show was if you calculated this in terms of x and y coordinates, that looks like the Laplace in terms of the Laplace in rectangular coordinates. So it's not a trivial problem. It's not easy to see that this is the Laplacian in polar coordinates. And even the way we show it, we do it backwards. We start with the right hand side and show it's equal to the left hand side, which is counterintuitive. One would think we'd start with this equation and then convert it, but we don't. We go the other way because it's not obvious. Someone figured it out and they wrote it down, and now we just do it this other way because the other way is just not easy. So here, very quickly, and I'll stop here very soon, and hopefully I can just get through this derivation real quick here. So our two basic chain rules. The partial of function of xy with respect to r. So here you have partial u, partial x, partial r, plus, plus partial u, partial y, partial y, partial r. And here now we use the fact that x equals r cosine theta and y equals r sine theta to find those partials. And so that's where you see this sine and cosine term here. We take the partial with respect to r. Oops, there's a typo here, my bad. This should say r sine theta, okay? So you take the derivatives, that's where these are coming from. And there's also a theta derivative. Again, it's partial u, partial x, partial theta, plus partial u, partial y theta, and that has this form. And so we've learned a bigger lesson here, that this is the formula for the derivative, for the r derivative of any function of x and y, not just u of xy, Again, here we've learned a bigger lesson that this is the formula for the theta derivative of any function of x, y. There's nothing special about u specifically. And so now what we can do is we can find a second derivative of u tilde, keeping in mind that this part ux here, this is a function of x and y. So this formula that we developed, we use iteratively when we do the second derivative. So yeah, I don't want to go through all the details too much because you did it as a homework problem, and I'll let you kind of work through it. Look, this plus I need to fix. This r missing here I need to fix. So yeah, and then we do the same thing with the theta derivative. And you go through the whole thing. I did a product rule and I show it all again. And then I take a second derivative. Then I divide by r squared. And it's, use some identities or something. And then combine it with all this other junk. And finally, you get this when you add everything. You get this extra term over here. Finally, move that over. And so now here, you get the two forms of the Laplacian in polar coordinates. So let's take a look at this. Here's the Laplacian in polar coordinates in terms of u. Here's the Laplacian in polar coordinates. Here's the Laplacian in polar coordinates again, and they're both two different, they're the same, but slightly different form. We can write this part as a product rule over here. So here, if you do this derivative and do derivative of the first times the second, plus the first times the derivative of the second, if you do that product rule, you'll get back this expression here. So typically the version that you'll see, most commonly is this version because it looks a little more complicated. So I guess people like to use that version. And so now, the Laplace U, we'll now try and solve this problem here using separation of variables. We'll assume U is a function. U can be written as a function of R times a function of theta, and then we'll try and solve that with the polar coordinates. And again, here I make this comment about the notation, and you can see here explicitly that if we just verbatim copy the formula for the Laplacian in terms of Cartesian coordinates, we do not get the formula we've derived here. That is the correct formula. So this version here is the correct, right? And this one here, this is just wrong. I mean, there's no difference there. There we just replaced one squiggle with another. We haven't actually changed anything. So yeah, so this is equal to U partial x plus U partial y, which is Laplace U. So, okay, folks, thank you for your time. I'm going to stop here. I will pick it up next time where we will start doing separation of variables for the polar coordinates. And that's the last time we'll do separation of variables. And then I'll just do a quick wrap up of all the PDEs we've seen. And then we're on to Fourier transform and dispersive waves. And then the project will start. So, all right, folks, I'm going to stop right here.